Hello everyone, so welcome to the final lecture of week 2. So in this week we have been discussing about deep learning fundamentals, and we will discuss a few more techniques in this lecture. So in this lecture we are discussing about gradient descent and initialization. So how do we initialize the parameters of a deep learning neural network, and what are the methods for updating the parameters, gradient descent and other such variations. So this is what we will be covering in this lecture. So let's first talk about initialization, because that is connected to what we were doing in the last lecture, right, on backpropagation and how do you update the parameters, right. So we wrote down these equations as the building blocks of neural networks. So in terms of pre-activations, we have the bias and the sigma k times the activation from the previous layer, and this gives me a function fk on which I can apply the activations, right. And this I can again write as beta k plus omega k activation over fk minus 1. So this is some sort of recursive formulation that you can see. So k written in terms of k minus 1 layer. Now at initialization, what we can do, so we can put all the bias terms to 0. And the standard practice is that I will choose the weights that are normally distributed, so mean is 0 and variance is some sigma omega square, right. Now the question that we will be discussing in initialization is what should be the value of sigma, what is the variance that I should keep in this. Now of course we can keep values of, typically we can just take unit variance, right, but what happens if we take the value of sigma to be very small or very large? What will be the impact on the learning trajectory? So we will see that in how the hk across layers, they vary, right. So the activations vary with changing this initialization. So what we have done, so this is a picture from this UDL book. So we have taken a deep network with 50 hidden layers. So there are 15 hidden layers. So you see on the x-axis layer from 0 to 50, and there are 100 hidden units per layer. And the network has a 100-dimensional input, and the initialization is done by standard normal distribution. The single output fixed at y equal to 0 and least square loss function. Now the bias vectors are initialized to 0 as we discussed, and the weight matrices, the omega k, are initialized with normal distribution, mean 0 again as we discussed, but we varied sigma the variance to 0.001, 0.01, 0.02, 0.1 and 1. So what happens as a result of that, right? So let's focus on the forward pass, right? Forward pass, when we are computing from the initial input to the first layer, second layer up to the 50th layer, we will compute all the activations, right. And we are seeing what is the variance of the activation for a kth layer as we go from 0 to 50. So initially, let's say all the variance is 1, okay, for the activation for the first layer, the k0 layer, which activation, the variance is 1. So what happens as we progress? So if we initialize the weight matrices with this variance as 1, so that is what we will assume to be a good value. What do you see? You observe that the variance for activation, it keeps on increasing, right. So at 50th layer, this will become something like here, to actually very high value. On the other hand, if we take a very small value like 0.001 for this variance, this will become very small. The variance will become very small. So what we would like the variance across layers to be constant, right. So where is the constant line happening? at 0.02. So if we had taken sigma square at 0.02, I would have got a very good initialization, because then as I am going in the forward propagation, the variance for activation remains constant, it remains at 1. Okay. Now this is desirable, it does not explode, does not vanish. And a very similar phenomenon happens in the backward pass also. So where you are computing the variance for the loss gradient with respect to the activation, dou L over dou Hk, and starting from the value 1, from the last layer we are going backwards. So for some values, like if I take the initialize at 1, this is exploding, like coming close to 10 to the 100. If I initialize to 0.001, it is vanishing, right. So you are either having exploding gradients or vanishing gradient. And where do you find a good thing? Where if I took 0.02, the variance remains constant across the layers. And what is the sigma 0.2? This is actually 2 by dh. dh is the number of hidden units per layer. This is 2 by 100, 0.02. So 2 by dh, so sigma square as 2 by dh turns out to be a very good initialization. This is also called Hay initialization. Now, but we will see what is the theory behind that, that why do we typically go for this particular initialization. Okay. So this is our aim, we want to keep the variance same across 2 layers. So I am going using beta plus omega h and getting a new function f prime. Okay. And I want it to follow certain property, like for example, what will be the mean of this if this pre-activation. So mean I can simply compute as expectation over beta plus omega h. Now we are anyway initializing beta is a 0, so expectation of beta I will be 0, and this term summation over j is equal to 1 to dh, expectation over this, right. Now here I can write it as a multiplication of 2 expectation. Now this we have anyway initialized as mean 0, right. So expectation of omega ij is 0. So 0 times anything you multiply, you will get a 0, right. So that means expectation, the mean for the pre-activation is 0, and that is what we wanted. We wanted this to remain constant. So mean is 0, but what happens to the variance at the pre-activation? So we know weights for distributed with mean 0 and variance sigma omega square. So let's compute the variance for the pre-activation sigma square, and we know the variance is expectation of this f I prime square, expectation of the variable square minus expectation of the variable square. So this is nothing but the mean, and we already computed this to be 0. So this quantity will become 0. So this goes away. I only have to worry about this expectation f I prime square. Now how do I compute it? I know this formulation f I prime is beta I plus summation j equal to dh, 1 to dh omega ij hj. So this is square of that. Now the term beta I, it will anyway has been set to 0, right. So bias is just 0. So this quantity will go away. So I am only left with this, right, expectation of this whole thing. Now for doing that, I can take this summation sign outside. Okay. So actually what would happen if you want to fully consider this, you will have square of these terms. So you will have sigma ij omega ij square hj square. So these kind of terms for all, plus cross terms, right. So you will have cross terms. So they will be 2 times sigma omega ij omega ik hj hk, these kind of terms, right. So for all possible j and k. Now if you will take expectation for this quantity, so you will find individually they are 0. So you will get 0 here expectation. So this quantity you can ignore. So what is remaining is the square terms, right. So you have for dh times, you have expectation of omega ij square and expectation of hj square. Now let us see what are these. Now expectation of omega ij square is the variance of this, so that is sigma square, sigma omega square, right? And then what is expectation of hj square, right? So then the only thing that you have to approximate is this, what is summation j equal to 1 to th expectation of hj square. So let us see what is this quantity, right? So we have to consider this. Now hj is nothing but ReLU of over fj, right? So ReLU over fj square, and then to compute it, I actually write this, I expand this. Expectation is nothing but is the probability distribution from minus infinity to infinity, ReLU of fj square, the actual quantity, times probability of fj dfj, right? So I am writing in terms of the probability distribution, fj dfj going from minus infinity to infinity. Okay. Now what is ReLU of fj? ReLU of fj is fj times an indicator function. If fj is greater than 0, then only it will become fj, otherwise it will become 0, right? So I replace that here, square PR fj dfj. Okay. Now this quantity will matter only if fj is greater than 0, otherwise this quantity will become 0, right, if fj is less than 0. So in this integral I go only from 0 to infinity, and I can ignore this indicator function any further. So I have fj square PR fj dfj. Now what is this quantity? Now let us say in the previous layer, the layer for fj, the variance was sigma f square. Yes. So what was that? So this was minus infinity to infinity fj square PR fj dfj. So this is sigma f square, right? Now by symmetry, so this is equal to minus infinity to 0 fj square PR fj dfj plus 0 to infinity fj square PR fj dfj, right? And by symmetry this will be same, right? This and this will be same. So that means each value is sigma f square by 2. So this will be sigma f square by 2, and this helps me to substitute the value sigma f square by 2 here, right? So that is the variance at the previous layer. So now I have everything I need. So this quantity I am adding dh times, so sigma omega square sigma f square dh by 2. That is the variance that I am having at the next pre-activation, and I want this to be same as sigma f square, right? So I want this to be same as sigma f square. So sigma f prime square is this, and to keep sigma f square prime square as sigma f square, I should have dh sigma omega square by 2 should be 1, right? This quantity should be 1, and that means sigma omega square should be 2 by dh, and that is where we get the Hay initialization, right? So if I keep this variance as 2 by dh, so number of hidden neurons 2 by dh in the next layer, so this gives me a good initialization, right? And this is a very popular initialization in deep neural networks. Okay, and actually there are other ideas in initialization. What happens if you go backward? It should be 2 by dh prime for the previous layer, and if dh prime and dh are same, they actually are the same quantity. If they are not the same, you could use 4 by dh plus dh prime. So that is typically considered a better initialization. So you take the the input layer and output layer of this weight matrix, take the neurons, and this will be 4 by number of neurons before and after, right? So that is a good initialization that you can use to take care of both forward pass and backward pass. Okay. So now let us talk about the gradient descent, right? Given this idea about initialization, so let us talk about gradient descent. So we have already discussed what is this algorithm. So you have the loss that you are computing, and you want to compute the derivative of the loss with respect to all the parameters of the model. Let's say if there are phi naught to phi n parameters, you will compute the loss with each of the parameters, and then you will update the parameters according to this rule. So, new parameter is previous parameter minus, you go in the negative direction of this gradient with taking a constant step alpha. Alpha is always a positive scalar, denotes the learning rate. So, this tells you how much change you will do. If you have a large learning rate, you will make large changes. If you have a small learning rate, you will make small changes. Okay. So let's take the example of the very first problem, linear regression. So we had two parameters, the intercept and slope phi naught phi 1, and let's say this is my initialization. At some phi naught phi 1 I initialized, right? And I want to go further, right, using gradient descent. So that means I have to compute the loss, the derivative of the loss at this point with respect to both phi naught and phi 1, right? So this was my loss function. So for all the I data points, fxi phi minus yi square, and fxi phi was phi naught plus phi 1 xi. So this becomes my loss. Now let's take a derivative of this loss with respect to both the parameters. So dou li over dou phi naught and dou li over dou phi 1. So if I differentiate with respect to phi naught, what do I get? 2 times this whole quantity, and phi naught has no multiplication, so only this much. And when I do with respect to phi 1, 2 times this quantity and xi. Right. So this is the loss for both the parameters. So now I will see what is the loss for both and what is the direction. So in this case, so with respect to phi naught and phi 1, so this is the two loss by phi naught and phi 1, and let's say this is the direction of the loss, right, given these two. So what I will do, I will go in the opposite direction of the gradient, right. So I will go in the opposite direction of the gradient, and how much I will have to multiply by the learning rate alpha. Right. So this is what happens. So I am going in the opposite direction of gradient, I am taking some step, and this is my new parameter. So parameter at step 1, the next iteration, so which has some phi naught and some phi 1, and I again apply this rule. I will find the gradient in both the direction, in both the parameters, the update, and find the direction, go in the opposite direction of the change. Right. So let's say I obtain like this. I go from second iteration, third iteration, fourth iteration, and in the parameter space you see my phi naught phi 1 are changing, and accordingly my fit is becoming better. So at 4 I am already making a better fit with the data. So this is what happens, right. So now let us take one particular example function and see what are the specific thing we have to consider while doing gradient descent. So this is our given model, so which is given by this equation fx phi is sine of phi naught plus 0.0651 x exponent minus this quantity by 8. So if you see closely, this function has only two parameters, phi naught and phi 1, and of course you have the input x, right. So phi naught phi 1 are the parameters and x is the input. Given these three, you can fully determine what is the value of this. So we will only consider this phi naught phi 1, and given x we will plot this, right. So we can see if we are getting good plot. So here for phi naught phi 1 you have this model, for phi naught phi 1 this value you have another model, and phi naught 3 and phi 1 15 you have another model, right. So given the data, we will know which of these values of parameters would be the best. So let us say, so suppose you are given some data points. So these are the data points in brown, right, and you can choose various values of phi naught and phi 1. So let's say you choose this value of phi naught phi 1. So your loss is 3.67. Similarly, this is a good value. You can see the loss is nearly this looks very black. So this is nearly 0. So this is 0.64. If you take this point, loss is 9.96. If you take this point, 10.18, and this point, loss is 5.51. So in this particular space of phi naught and phi 1, you can have various losses at different point, and I would ideally want to achieve somewhere here, right. So a very small loss, and you can see I am very nicely fitting the data with this K-bar model. So I am looking for this value of the parameters, but I don't know, I just have the data point. So I have to start randomly from somewhere and hope to be able to go to this point using gradient descent algorithm. Now that's where the problem happens. So you may have multiple minimas in your loss function, right. So it's not that this is the only minima. So, because the loss curvature is very complex, you will have local minima also, you have minima at various points. So, for example, this point looks like a local minima, right. So, what would happen because of these multiple local minima? So, if you actually start in the right valley, so like if you start 1 and you follow the gradient negative gradient direction, you achieve this point. Similarly, if you start in 3, you follow this, so you achieve here. But on the other hand, if you start at this point, right, they are very close, right, they are very close point, and you follow negative direction of gradient, you may achieve a local minima. And once you achieve a local minima, it will not be possible for you to go back to global minima by this method, or you can stuck near a saddle point where there is a change in the gradient, right. So, these are some known issues with the gradient descent. So, you can, because what happens in gradient descent, you compute the loss with the entire set of data that you have, training data, and then you go take one step, right, and you keep on doing that. So, it is very deterministic in which the trajectory moves, and if you have not started at the correct point, you may end up with a local minima and may not achieve the global minima. So, one option of course is that you can start again, right. So, you can take multiple points and keep on starting again and again. So, that is one possibility people do. So, you have started from one point, you try starting from another point and see if you achieve the same minima or you achieve something better, right. So, that is something you can do. But there are some other ways of avoiding this, right. So, which in addition in theory they can avoid this local minima, and one particular method for this is a stochastic gradient descent. So, gradient descent goes in very deterministic manner. Once you have a starting point, you will compute loss gradient for the entire batch and keep on loss for the entire batch and keep on going the negative direction. So, what happens in stochastic gradient descent is, so you do not compute gradient for the entire data, you just select a random subset of points, and this is what you call it mini batch. So, let us say you have 1000 training data and your mini batch size is 10. So, that means you will randomly select 10 points from there, and for those 10 points you will accumulate the loss, compute the derivative of the loss and go in the negative direction of that, and then you keep on doing that. So, you again sample 10 from the remaining 990. So, it is without replacement, so that each data point is equally sampled, right. Again you will do 10 samples as your new next mini batch, and when you have made the complete pass, like you have done 100 batches, it is called an epoch. You have gone through the entire data once, that is an epoch, right. So, here you are adding some noise, because what is happening, so in gradient descent you are going through the entire data and computing the loss, right, that will be always fixed value starting from a point. But here, because you are using some random mini batches, it may happen compared to the overall scheme of things, some mini batch can take you the other direction, like the uphill from the entire batch, right. So, and they can take you from a very different trajectory, because different samples may have different kind of loss functions. I mean, loss function is same, but the loss that you will get may be different. So, in full batch descent, this is what you do. So, the parameter t plus 1 is parameter t minus learning rate, and you accumulate the loss over all batch. In SGD, you only accumulate over a batch. So, BT denotes a particular mini batch at time t, right, and learning rate is fixed. So, the trajectory becomes very different, and you can see the noise coming in, right. So, you started with 2 here and you reached the local minima, but here you could avoid it. So, because it will depend on the particular mini batch. So, you took this direction, this direction. So, you keep on taking directions and you actually ended up going back to the global minima. So, in principle it has been seen that stochastic gradient descent can escape local minima in principle, because if you had started at this point, gradient descent would not have escaped it, but SGD could. And it has some nice properties. I mean, you still have each data point contributing equally, and because you are taking a mini batch, it takes little it's more efficient, it's become faster to do one particular update. So, here you have to wait for the entire batch, but here you can update quickly, right. So, it has some nice properties. So, although there is no guarantee that it will converge to global minima, in practice it is seen that this is much better in avoiding the local minima, and that's why stochastic gradient descent is much more popularly used with training of models. Now, one issue with that is of course, the zigzag trajectory of this loss, right. So, you do not have a very nice trajectory like you were seeing here. So, what can we do to obtain go back to the same a little more smooth trajectory, and that is where we try to add momentum, right. This is again a very interesting concept. So, what we do, so it is like you are going in some direction, like your gradient was in some direction here. Next time you don't want to completely change the direction, you obtain the gradient, but you still want to go in the previous direction. So, you take a weighted sum of the previous gradient and the next gradient, and you keep on doing that. So, that means your gradient the new time point is beta times the gradient in the previous time point plus 1 minus beta times the actual loss term. So, in a stochastic gradient descent you would have simply used this term in SGD, but now in momentum you are adding also the some factor of the previous gradient, right, and then you are updating parameter with. So, this is one particular common modification to SGD, that you add this momentum term, and this typically helps. And because this is such a recursive formulation, what happens? So, it is like you are having an infinite weighted sum of all the previous gradients, right, and as we keep on moving in time, so the weights get smaller and smaller. You can see beta times MT, and MT is again beta times MT minus 1. So, you have beta square, beta cube, and typically beta will be less than 1, right. So, you keep on getting exponentially smaller and smaller weightage from the previous gradients, but you make use of all the gradients that you have seen till now, right? And this is what gives you a smooth trajectory. So, this is when you had no momentum, and you can see how the zigzag the trajectory is, but when you add momentum it becomes much smoother, because now you are going in the previous direction plus adding the new direction. So, this becomes much more smooth. So, that is why momentum is typically preferred in training the models. Now, even with momentum, if you just use momentum, you still have certain issues, right. So, what happens? So, suppose you were using a fixed learning rate alpha, right. Now, the loss across different parameters may not be varying similarly. So, some parameters may be some direction may be very steep, right. So, it may happen the gradients are steeper in one direction than another. So, what would happen if you use a very small learning rate, let us say 0.05, very small learning rate. So, wherever the gradients are steep, you will make some progress, but in the other direction you will not make any progress at all, you are not making any progress, right. On the other hand, if you use a large learning rate, so you are making progress in both the directions, but in the direction where it is steep, you are having huge oscillations. So, you are having huge oscillation, also you are making progress in that direction, but here you are having huge oscillations, right. So, you are doing a large adjustment to parameters with large gradients, and wherever there are small gradients, you are doing very small adjustment. So, this is something that can be avoided, that can we somehow try to normalize the gradients. So, how can you normalize the gradients, right? So, one very simple way could be that I simply care about the direction of the gradient and use a fixed learning rate. So, that means that the gradient in all direction will change by the same amount, but the direction will matter, right. So, that is one formulation, that you normalize your gradient. So, how can you do that? So, I have my gradient at time t plus 1, I compute the square of that, right, and then the actual change would be mt plus 1 divided by square root of this, which plus epsilon. Epsilon is just to ensure in case this is 0, I am not dividing by 0. It is a small constant to ensure that we do not divide by 0. So, so it is as if you are doing mt plus 1 divided by square root of mt plus 1 square. So, you are just retaining the sign, right, otherwise magnitude is same. So, let us say these were the 3 values for 3 different parameters. So, the Vt plus 1, the square of this will be 9, 4 and 25, and once you divide it by this, and let us say epsilon is very close to 0, you get 1 minus 1 and 1. So, that means you are retaining the direction, but otherwise they are normalized, they are the same value, all the three, right. So then what will happen in this case? So now you will make equal progress in all the directions, right. So irrespective of how large or how small the gradient were in one direction. This is nice. So this curve looks quite good, right. You're not having very high oscillations. The problem is that because you have fixed how much you will make progress in each direction, if it does not land on the exact point of minima, it will just keep on oscillating around that. It will not converge, right. It may not converge unless it lands on that exact point, and you will keep on making these small whatever changes that you wanted to make. So how do we ensure that it actually converges? And that's where the very famous algorithm ADAM comes in, adaptive movement estimation, which says, okay, just like we did the momentum for the gradient, we can also compute the momentum for this Vt plus 1 term. Right? So you compute mean and pointwise square gradient with momentum. Right? So mt plus 1 will be beta times mt plus 1 minus beta, the actual thing, and Vt plus 1 is gamma times Vt, the previous time squared one, plus 1 minus gamma this. And I will still not use that. I will use my parameter update is phi t minus learning rate times m hat t plus 1 divided by square root of Vt plus 1 plus epsilon, where m hat t plus 1 is mt plus 1 divided by 1 minus beta to the power t plus 1, and V hat t plus 1 is beta t plus 1 minus divided by 1 minus gamma to the power t plus 1. And as you can see, as you keep on going further and further, these values will be like 1 minus beta 10, 1 minus beta 100, and because beta is smaller than 1, so this will go close to 0, right, as you keep on going further and further. So you would start using it, but at the beginning you would have a high moderation, so mt plus 1 divided by 1 minus beta, right. And this particular method seems to avoid this problem of oscillation, and you make a nice smoothly you can go to and converge. So this is with alpha is equal to 0.05, but beta and gamma chosen as some constants. So ADAM is typically one good method that people use for training deep learning models. Of course, I mean, when you are training a deep learning model, you have lot of hyperparameters. So for example, what is the learning algorithm that you will use? Stochastic gradient descent, just momentum, ADAM, ADAGRAD, and so on. What is the batch size that you will use? Right? We talked about batch size, but how big or how small? Learning rate schedule. So many times what happens, so people have seen, if I keep the same learning rate alpha, it doesn't help, because initially you want to explore the parameter space a lot, but after the initial exploration you want to converge. So you want to decrease. So you want to decrease after some initial period, decrease learning rate gradually. So there are various schedulers that you use for learning rate that make sure that the learning rate decreases over time. So this is again a hyperparameter, that what is the schedule that you will use, and if you're using momentum, what are the coefficients, the beta, gamma, etc. that you will use. So they are all hyperparameters, and there is no nice way of telling what hyperparameters actually work best. So what typically people do, so they will train many models with different hyperparameters and see which one works best on the validation set. So this is known as a hyperparameter search, and you would use a validation set for finding out the best set of hyperparameters, right. So this is one integral part of training the deep learning models. So in this week we have discussed few important concepts about deep learning, starting from shallow networks, deep networks, backpropagation, learning, initialization. And there is of course much more to deep learning that we have not talked about in this week, but we will gradually cover whatever is needed in the subsequent lectures for NLP. In the next week specifically, we will start with the very important idea of deep learning, that is, how do you learn representations. So how do you learn representation for a word, right, or even we will go gradually over the weeks from word to sentence and so on. How do we learn representations, right, at a different granularities. So that is what we will do next week, and for this lecture you can go through chapter 6 and chapter 7 of this book, and of course you can explore this book a lot, because this talks about deep learning, and that would be highly beneficial. So with that we can end this week. Thank you.